and my metric number is 211131. I am the group leader for group 5.
Hello, my name is Dimitri Gandhan and the matrix number is 212219.
Hi, my name is Muhammad Faiz bin Adnan and my metric number is 213065.
Hi, my name is Noala Nabila binti Azmi and my matrix number is 210245.
Hi, my name is Hanis Adra binti Zulkifli and my matric number is 211238. We are from Group 5 have decided to choose Faraday law as our topic to discuss, and let's look forward to it.
Michael Faraday was a British scientist who made a significant contribution to a field of electromagnetism and electrochemistry. He was born in 22nd September 1791 in Newington Butts, England. Faraday received only a basic education as he had to leave a school at the age of 14 and work as an apprentice to a bookbinder. Despite his lack of formal education, Faraday was a curious and intelligent young man who was really interested in science. In 1812, he attended a lecture by a chemist, Sir Humphrey Davy. Then, Faraday sent a bound of copy of his note to a Davy, along with a letter of employment. But there was no opening by Davy. However, when one of Davy's laboratory assistants was dismissed, Davy offered Faraday a job as he was impressed by a Faraday patient. So this is how the Faraday career in science began. So while Faraday was working at the Royal Institution in London, Faraday studied the behavior of magnetic field and the interaction with electrical conductor. This led him to formulate a hypothesis about how a changing magnetic field could induce an electric current that ran through the nearby conductor. So to test his hypothesis, Michael Faraday had conduct a series of experiments using a coil of wire and a magnet. So he found when he moved the magnet into and out of the coil, an electric current was induced in the wire. Finally, he successfully discovered the magnitude of current was dependent upon the number of lines of force that cut by the conductor in unit time. However, Faraday did not stop his investigation there, but also continued his research into electromagnetic induction, and he found a key of observation which have led to the concept of magnetic flux. So in 1834, he discovered the amount of induced current depend not only on the rate change of the magnetic field, but also depend on the size, shape, and orientation of the conductor with respect to the magnetic field. Okay, so I think that's all about the background story of how Faraday discovered the induction law.
Assalamualaikum and a very good morning to everyone. So today I would like to present about the Faraday first law of electromagnetic induction. So here is the content on how I will distribute the definition, method, and conclusion during this presentation. So first of all, we will talk about the definition. So definition of the Faraday's law of electromagnetic induction is a basic law of electromagnetism where it is predicting how a magnetic field will interact with an electric circuit to produce an electromotive force EMF. So an EMF is induced when the magnetic flux across the coil changes with time. So here is the ways on how we can change the magnetic field intensity in a closed loop. So the first step is by rotating the coil relative to the magnet. And the second one is by moving the coil into or out the magnetic field. The third one is by changing the area of a coil placed in the magnetic field. And the last one is by moving a magnet towards or away from the coil. So to get more deeper into Faraday's first law experiment, I will explain to you how it works. So consider that the north magnet pole moves toward the coil. Upper end of the coil acquires north polarity, hence work is done against the force of repulsion to move the magnet. So if the magnet is withdrawn from the coil, upper and acquires soft polarity, so work is done against the force of attraction. So now we know that as the magnet moves through the coil, magnetic flux linked with the coil change induce a current. The direction of the induced current is found from Lenz's law. So the work done in moving the magnet towards the coil is converted into electrical energy, which gets dissipated into heat energy. So the current flows in a direction to oppose the motion of the magnet. If in case the induced current promotes the motion of the magnet, it starts moving at a faster rate and the electric energy induced and kinetic energy of the magnet starts increase. So I hope you all can understand how it works. I think that's all from me. If you guys have any question, you guys can ask in the next discussion part. Thank you.
Assalamualaikum and good evening everyone. Today I will talk about Faraday's second law of electromagnetic induction. This will be the content of my presentation. The first one, I will talk about the definition of Faraday's second law of electronic magnetic induction. The second one, I will talk about and explain about the formula that are used in Faraday's second law of electromagnetic induction. And lastly, the third one, I will talk about the real-life applications of the Faraday's law in where it is applied in electronic field devices. So we begin with our first point, which is the definition. So the definition says that Faraday's second law of electromagnetic induction states that the magnitude of the electromotive force, which is known as EMF, induced in a closed circuit is directly proportional to the rate of change of the magnetic flux through the circuit. In other words, the greater the rate of change of the magnetic flux through the circuit, the larger the induced EMF. Okay, so for the next one is the formula. Mathematically, Faraday's second law can be expressed as EMF equal to minus d phi over dt. To elaborate about the formula, EMF is the induced electromotive force, phi is the magnetic flux, and d over dt is the rate of change of the magnetic flux. The negative sign indicates that the induced EMF creates a current that opposes the change in magnetic flux through the circuit, as described by Lenz's law. Now, for my last point in my presentation is the applications in real life. The first one is power generation. Faraday's law is the fundamental principle behind the working of electrical generators. When a conductor is rotated within a magnetic field, the changing magnetic flux induces EMF in the coil, which can be converted into electrical energy. This principle is used in power plants to generate electricity. And for the second example is the transformers. Transformers are devices that utilize Faraday's law to step up or step down the voltage in an alternating current, which is known as AC system. By varying the number of turns in the primary and secondary coils and the rate of change of magnetic flux, transformers can efficiently transfer electrical energy between different voltage levels. To conclude about the Faraday's second law, we can say that overall, Faraday's second law of electromagnetic induction establishes a relationship between the change in magnetic field, the rate of change of magnetic flux, and the induced electromotive force in a conductor. It is fundamental principle underlying the generation of electricity in devices such as generators and transformers. That's all from me for my presentation in Faraday's second law of electromagnetic induction. Thank you.
Hello everyone, today I would like to share the application involved in electric guitar. First, let me explain how electric guitar works. Functions based on the Faraday's law of electromagnetic induction. What is electromagnetic induction? Occurs when there's a change in magnetic field and it induces electric current or voltage. Before I explain about the application of Faraday's law, let me move on to the components involved in electric guitar. Pickup is when the steel of strings of guitar vibrate, they create a magnetic field. For the amplifier, this magnetic field induces a small electric current in the coil of wire, which is then sent to the amplifier. Let's see how electric guitar works based on Faraday's law. First, electric guitar is made up of metal or ferrous material. Inside each string, there is a magnet. Those magnets are surrounded by a coil. This system is called a pickup on electric guitar. When a string struck, it vibrates the air around it. The vibration creates a disturbance in air molecules. The movement of air molecules is the sound we perceive from electric guitar. Another important part is when you strike the string, it not only moves the air around it, but because the metal string is magnetized by a magnet, this vibration will change the magnetic flux around the magnet. What happens when magnetic field is changing? Magnetic flux is changing, electric current is produced, which discovered by Michael Faraday. So, when you strike the string, it changes magnetic field, producing electric current, then goes through the coil and into the wire that is connected to the guitar pickup. This wire takes the electric signal which represents the wave created from the strike of the string, where it can be modified for the sound. The signal is then fed to an amplifier which makes the sound larger. After that it goes to the speaker and speaker radiates the unique sound we hear from electric guitar.
So I will start about simple question that related to Faraday's law. So the question is about a rectangular coil of length 0.5 meter and width 0.4 meter has a resistance of 5 ohm. Is placed with its plane perpendicular to a uniform magnetic field of induction 0.05 Tesla, and the magnetic induction is uniformly reduced to zero in 5 times 10 the power of negative 3 seconds. So the question here, it asks about what is the EMF induced and the current induced in the coil. So according to the Faraday's law, a changing magnetic flux produces an EMF in closed path for circuits, and on the other hand, magnetic flux is also the product of the magnetic field area and cosine of the angle between B vector and a unit vector to the normal plane. So in this question, it gives you a length of coil, width of coil, and the resistance of coil. It's still clearly here. And here it show you the initial magnetic induction where I call it as B1 as a vector is B. And the final magnetic induction where it said that the magnetic induction is uniformly reduced to zero. So here I say that final magnetic induction is equal to zero where it is B2. And then the difference of time where is given, where is also given. So how we calculate this question is first we calculate the area of coil where length times width where we get 0.2 meter the power of 2, and here because it doesn't give the coil have resistance, so I assuming the coil has a singleton, which is n equals to 1. So after that, we need to calculate the initial flux, where the formula is NAB1 cos theta, where N is the turn of the coil, A is the area, and B1 is the flux, is the magnetic flux. So the theta here is the direction of the normal plane and the magnetic flux. Here in this example, the area and magnetic flux are fixed, but the direction is changed, where because it is a closed loop circuit, so it's moving. Thus, I consider initially field and the normal plane was parallel, where I can say the theta 1 is equal to 0, and after some time, the theta 2 is 180. So here I use the cos 0 degree, where I calculate it, I get it 0.001 Weber. And then the final flux, where I use the second magnetic flux, which is 0, where we can say that the magnetic induction is uniformly reduced to 0 in 5 times 10 to the power of -3, where this is the end of the flux after the plane was changed to 180 degree. So we can see that these equations becomes to 0 Weber. So we need to calculate the change in flux, where the final flux minus the initial flux, where we get negative 0.01 Weber. And then to calculate EMF, we need to use the second law of Faraday's second equation. We need to use the Faraday's second law. So here we can say that it needs to use negative the difference of the magnetic flux divided by the time. So here I use the 0.01 Weber divide by 5 times 10 the power of -3 with the sign of negative here. So I can get 2 volt, and then I can calculate the current induced using the Ohm's law. So here I answer the question, where I get the EMF induced in coil is 2 volt and the current induced in coil is 0.4 ampere. So I think that's all from me. I will pass to Taki, and he will talk about how Faraday's law related to other law. Thank you.
Tu. Okay, since everyone have present their part, so now we are going to continue with the Q&A. So anyone have a question that relate to our topic?
Yeah, I have a question. So based on your explanation on Faraday's second law, Faiz, I want to ask you, what are the benefits of invention related to the Faraday's second law? Can you explain on that?
Okay, Rines, so to answer your question about the benefits of invention related to Faraday's second law, the first one are electric motors. As you know, Faraday's second law is fundamental to electric motors. Motors can convert electrical energy into mechanical energy, enabling the operation of numerous devices such as industrial machinery, household appliances, electric vehicles, and many more. The next one is transformers. Transformers utilize Faraday's second law to transfer electrical energy between different voltage levels. They are used extensively in power transmission and distribution networks.
enabling efficient long-distance transmission and minimizing energy losses. So transformers play a vital role in delivering electricity to homes, business, and industry. And for the last one is magnetic resonance imaging, also known as MRI. So MRI machines use Faraday's second law to produce detailed image of the internal structures of the human body. The way it works is it creates a strong magnetic field and inducing electromagnetic signals in the body's tissue. So MRI technology enables a highly accurate diagnostic imaging for medical purpose. That's all.
I see. That's a good explanation, guys.
Okay, Dinesh, I have a question about the application. You have present about our topic is about the electric guitar, right? So I want to ask if there any other technology that use the Faraday law instead of the electric guitar.
Yeah, there's a quite number of application uses in life. For example, we use wireless charging because every day every person uses wireless charging nowadays. Like this kind of technology used in smartphones, and this is very useful in Faraday's law. And apart from that, we can also use the magnetic type cards. Everyone use the debit cards, credit cards, and this kind of access cards have magnetic stripes on its back. So this kind of information are encoded in this card, so that this when we swipe the card in the ATM machine or any kind of bank transformation, this kind of magnetic fields pass over the information that utilizes the Faraday's law. And besides that, it also uses some this kind of application of Faraday's law is widely used in electric power generation, that's called power plants in our daily lives. This kind of power plants generators are used that employ the principle of electromagnetic induction, and this kind of electric power generation is widely used to convert the mechanical energy into electrical energy. So that's what I think kind of application is widely used in these types of daily life application.
Okay, Dinesh, I think there's a more application that use Faraday law in our life. I just know that. Okay. Anyone want to ask something?
I have a question about the introduction. So I am not clear about the first and the Faraday's law because it's a bit confusing for me. So what is the difference between the first and the second law? Can someone explain to me what about this? Can you explain?
I will explain to you the differences between the Faraday's first law and the second law. So basically, Faraday's first law is explaining to us about the electromagnetic inductions, where there is a change in the magnetic field passing through the conductor, and also electromagnetic force, which is EMF, is induced in the conductor. So this induced EMF cause an electric current to flow if the conductor forms a closed circuit. For the second law, as presented by Alice, it is saying that by the second law of electromagnetic induction, expand upon the first law by introducing the concept of magnetic flux. So it says that the magnitude of the induced EMF in the conductor is equal to the rate of change of magnetic flux through the conductor. So to be summarized, Faraday's first law focus on induction of EMF in the conductor due to the changing of magnetic field, while the Faraday's second law is quantitatively relates the induced EMF to the rate of change of magnetic field. So this law forms the foundation of electromagnetic induction, and I hope you can understand the differences between that. Did you get Alia?
Yes, sure. Thank you, Anis. So I think we can move to the next question. Anyone has any question?
I have a question for you, Alia. So do you think there are any limitations or practical considerations when applying Faraday's law in various applications?
So thank you, Faiz. So I think there are several limitations and practical considerations when applying this law. So the first limitations is about the ideal conditions, where the Faraday's law assumes ideal conditions which may not be met in practical applications. So temperature, pressure, and impurities in the system can affect the accuracy of the measurements. And then about the mass transport limitation, where in some case, the rate at which reactors are transported to or from electrode surface can become a limiting factor. So this factor can result in reduce the efficiency and deviations from the expected values predicted by Faraday's law. So then the next one is about the mass and charge transport, where the Faraday's law assume efficient mass and charge transport within the system. But in some applications, such as electroplating and electrochemical reactions in porous material, mass and charge transport can be limited, affecting the accuracy of the measurement. So I think it is clear about the limitations and practical considerations in the applications, right, Faiz?
Yes, thank you, Alia.
So before we end, anyone have any last question? Anis?
Can
Okay.
question to Actually, maybe it's about the Faraday's law background. So is there any law or equation that relate to Faraday's law?
Oh, there are two things that I think I found related to the Faraday's law. So the first one that I found is the Lenz's law, which is similar to the Faraday law, where the Faraday tell us about the magnitude of the EMF produced. Meanwhile, the Lenz's law tell us about the direction of the current flow. So it's quite similar. Just Lenz's law told about the direction of the current that will flow when it have induced. So this basically means that any magnetic field produced by an induced current will be in the opposite direction to the change in the original field. And then the next is a Maxwell third equation of electromagnetic field behavior. So according to the Maxwell Faraday equation, the curl of electric field is equal to the negative time derivative of the magnetic flux density. So based on this equation, show that the charging magnetic field may create an electric field, this is important to understand the propagation of the electromagnetic wave. So that is the two things that I think related to our topic, which is Faraday law. Okay, I think that's all from us. Thank you, guys.